Hello everyone, my name is Tianqi Tang from University of Southern California. It's a great honor to have the chance to present our work at ISMB 2022. The topic of our work is phage-bacteria contig association prediction with a convolutional neural network. One of the most important things in studying a microbial community is the phage-host association. However, in metagenomic studies, the host information by nature is lost for phages. Therefore, we have to develop a computational method to infer such association. Existing methods can be split into two classes. One is assigning phages to a certain taxonomic level. For example, given a phage sequence, you can predict its host to be a particular species, class, or phylum, but for these methods, they cannot directly study the relationships between contigs in a microbial community. They are only using the phage information, and the host information in the process is lost. The other methods directly compare phage and host genome to give a score. Where host matcher uses D2star to compare the KMA frequencies between phage and host. Which uses Markov model to make the comparison. They performed well when they were used on the whole genome of phage and host, but in our test for contigs, their performance degraded significantly. So our objective is to develop a computational method to predict phage-host association with only contigs with high accuracy. We developed a 4-path convolutional neural network. It takes two inputs, one virus sequence and one host sequence. The sequences are converted into two one-hot matrices, and each input is further split into two paths, one base path to parse the base information and one codon path to parse the codon information. You can refer to our paper for the detail of each path. The output of the convolutional layers are concatenated and fed into the full connected layers and finally get a result to indicate the association probability. We know that contigs can have different lengths. A regular neural network can only accept fixed length inputs. To solve this problem, we added a global average polling layer at the end of each path, so that for contigs with arbitrary length, there will be only fixed length output for each path, so that they can be fed into the full connected layers. The final adjustment we made with this network is that for virus and host, we forced their convolutional layers to have the same weight. The rationale behind this is that the convolutional layers in a network are usually considered as the fish extractor. For this particular task, we were not sure if we should have the same extractor for both the virus and host, or have a different feature extractor for virus and host respectively. So we tested both of them on the validation set, and empirically we found that by forcing them to have the same weight, we will have a higher prediction accuracy, and therefore we chose the first one to force them to have the same weight. The dataset we used in this study for training and validation is virus-host-DB. It gathered information from RefSeq, GenBank, UniProt, Virozone, and manual curation. We collected the data on March 2021. The dataset itself already included the virus sequences, and we downloaded the host genomes from GenBank. Therefore, we removed all hosts not from the GenBank. Finally, we get a dataset with 2589 phage host pairs, including 2548 phages and 301 host species. The distribution of the species is at the right. As we can see, E. coli still dominates. However, it does not overly bias towards any species, so we can use this dataset without any further modification. We first clustered the phage genomes with CD hit to remove any possible redundancy in the dataset. We clustered them with the parameters shown on the screen and got 2,300 clusters. For each cluster, we randomly selected a genome to represent the whole cluster. For each host species in the dataset, we downloaded the assemblies from GenBank. And if there were over 10 assemblies available, we randomly selected 10 assemblies and downloaded them. Because for some species such as E. coli, there were over 20,000 assemblies available on GenBank, and it is not possible for us to just download all of them. In each training epoch, we randomly selected one assembly to represent the species. We then split the dataset into 80% training set and 20% validation set. Any phage host pairs with overlapped phage or host were moved to the validation set. The possible phage and host contig lengths are shown on the screen, and for each training epoch, we randomly selected one phage contig length and one host contig length, and then sample the contig from the whole genome according to the given length to construct the batch. In the training, we also need to construct the positive and negative phage host pairs. For the positive pairs, they are directly retrieved from the virus host DB, and for the negative pairs, we used a fairly straightforward way to randomly select host species that are not reported in the virus host DB. And we kept the positive and the negative ratio to be 1:1. The hyperparameters used to train the model is shown here, and the AURC was used to assess the performance of the trained model. As for the result of the testing, I would like to first quickly remind the weight-shared dipath neural network by forcing the convolutional path for phage and host to have the same weight. Here we can see that the shared weight network outperformed the distinct weight neural network. The possible reason for this result can be either easier convergence for the training or the better generalizability of the network by forcing them to have the same weight. We also compared ContigNet to traditional methods D2* and Wish. We can see that even for longer contigs, as long as 50 kilobases, compared to their performance on whole genome, D2* and Wish still performed very poor, getting only 68% and 67% AURC score. In contrast, for ContigNet, even for contigs with only 200 base pairs, we still got 71% AURC, which is much higher than the traditional methods. In the previous slide, we noticed that with longer contig, we can get higher accuracy. So we tested how exactly the contig lengths can affect the AURC score. We tested our model on contigs with different contig length combinations as shown on the screen, and we observed an apparent trend that with longer contigs, we tend to get higher score. However, the score converges at around 85% with 5,000 base pairs, and longer sequences were not able to further increase the score. Our method will ultimately be applied to real metagenomic samples. However, in metagenomic samples, there can be multiple sources of errors. For example, sequencing errors and assembly errors. So we introduced artificial sequencing errors and assembly errors to the validation set, and we'll see how they will affect the performance of our method. For the sequencing error, the insertion, deletion, and the substitution rate can all be as high as 10%. You can refer to our paper for the details of how the experiment was conducted and how the error was introduced. For assembly error, we exchanged from 0 to 20% of a contig with any random contig in the validation set. We also kept the exchange between only phages and hosts. The results are shown in these two figures. With no error, the AURC was around 84%, so we used it as our baseline. We can see that with severe sequencing or assembly error, the AURC will drop. However, even with the most severe error, we still maintained over 80% AURC, indicating the robustness of our model to such errors. The virus host database gathered information of viruses with higher completeness and whose host information were identified in experiments. We wanted to see how our method performed on real metagenomic data. So we used metagenomic gut virus MGV catalog. It collected over 11,000 distinct human gut metagenomic samples. This database assigned viruses with over 50% completeness to hosts with CRISPR spacer matches and whole genome alignment. These two methods have high specificity and low recall compared to identification with the experiments. And finally, it has around 77,000 phage host pairs. Any overlapped phage or host pairs between the MGV catalog and the virus host DB were removed. We can see that for the real data, there is a sharp drop compared to the validation set. However, even for the shortest contig pairs, we still maintained 60% AURC and got around 70% for longer contigs. Considering how the host was identified in this dataset, a lot of false negative pairs might exist in this dataset, further lowering the score. Comparing to traditional methods, D2-star and WISH, I'm not showing the figures of the results of them because even for the longest contigs, they were not able to tell the difference between positive and negative pairs, and getting only 50% AURC score. So our method is actually a lot better than the other methods. Of course, our current result is still not ideal, therefore we need to find a better method so that it can get a better score on a real metagenomic dataset. We also compared CONTIG-NET to other available methods in whole phage genome taxonomic assignment. We did it by comparing the whole phage genome to the whole host genome and try to assign the phage to a particular host and calculate the accuracy at each taxonomic level. We can see that our method cannot compete with other state-of-the-art methods on this task, which was expected because our method was not designed for this particular task, so we need to choose the tool wisely according to what particular task we are doing. In conclusion, CONTIG-NET performs better than all existing methods for the particular goal of phage-host contig association prediction. Based on the result on the metagenomic dataset, however, we can see that the accuracy can still be further improved. CONTIG-NET is a good complementary to the current metagenomic toolsets in studying the dynamic of microbial communities. Actually, our collaborator is already using it to study the Southern California coastal metagenomic samples. For the acknowledgement, I want to first thank my advisor, Fengzhu Sun. He taught me a lot in the whole process of research. I also want to thank our collaborators Shengwei and Jed. They gave me a lot of great advices in experiments and writings. I want to thank the faculty and staff in the school and also NIH and NSF for the funding.